All right, let's talk about 9.3. We've talked in 9.1 about sampling distributions in general. In 9.2, we talked about sample proportions, and now we're going to talk about sample means. And the two big ideas from this section. If you look at a sample of more than one at a time, look at them two at a time, or 10 at a time, or 30 at a time, and then you were to record in a sampling distribution the outcomes of repeated sampling, those averages will be less variable and more normal than the individual observations. In other words, they will be less variable and more normal than the population in general. So let's say you have a population that looks like this with the skew to the right. If we were to look at this thing two at a time, say this is n equals 1. This is basically the population. If we were to look at it two at a time, and let's call the center right here at C. The center's been pulled a little bit to the right of the peak by that skew. The bigger the sample, the more normal we will get, and the more tightly packed we will get around C. This is a good picture of this in your book we'll refer to. But the idea is this. The more you can look at, the more certain you can be about your results, because the more normal and the less spread out your curve will be. Just like in 9.2, this is all based on one point. The center is going to be the population center, just like the sample proportion was the same as the population proportion for our distribution. It's similar with means. The only difference is we need to adjust our standard deviation, just like we did with our proportions. So, mu x bar, this stands for the average of basically all the averages. This is the average of all of the little sample averages. So, mu x bar is equal to mu. Meaning, if the average person is 60 inches tall, and I look at samples of size 100, I should, when I average up all those samples, I should stay close to 100. Now, the thing that's going to change is the spread. I'm not going to, let's say I have a population of people anywhere from 40 to 70 inches tall, and the average, the middle of that's 50. I'm not going to look at 100 people at a time and get an average of 40. Just like in class when we looked at that example, you're not going to get all the extreme high or low numbers if you look at 100 at a time, or the probability of that happening is very low. Basically what happens is if you look at 100 at a time, you're going to get some high, some low, some middle, and they're going to all average out to what's the middle of your population. The difference, again, is the spread. The standard deviation of x bar is equal to the population standard deviation divided by the square root of n. So again, n being on the bottom tells you if you ask more people, your spread actually goes down, which is why this pattern above is what's going to happen. Right? Because it's square rooted, if you want your spread to be half as much, you need to ask 4 times as many people. So now let's check an example. Right, so I'm just going to make one up on the spot here. Let's say, for example, the average miles on all cars in Lexington is, I don't know, 48,000. With standard deviation of, again, I'm just estimating, let's say 17,000. No idea if that's anywhere close to accurate. Here's the beauty of this, what's happening in this section. It doesn't matter if this distribution is normal or not, because if we look at a sample, and as long as that sample size is big enough, we're going to be taking an average of a bunch of cars, and those averages are more normal than the individuals. So in some of the problems, they'll tell you that your population is normal early on, and then we're going to learn something we'll talk more about in class called the central limit theorem, which basically says it doesn't matter if your population is normal or not. If you look at a big enough sample, you can use normal calculations because repeated sampling would lead to a normal distribution. So let's see. If I sample 100 cars, assuming it's a simple random sample and all the conditions are okay, I haven't done anything fishy, what's the probability that my average is, let's say, greater than 50,000? So just kind of think about what you're being asked here. If you were to go out and look at one car, mine for example, my Hoopty, does it have more than 50,000 miles? It does, and I'm not surprised because I'm just looking at one car. If you were to go out and look at 10 cars and you average their mileage, would you be surprised if it was over 50,000? I don't know. We would expect these averages, these repeated averages, to be closer to 48,000, but is 50,000 really that rare if we're looking at 10 at a time? You could throw one car in there with 150,000 miles and probably make that happen very easily. But what if we look at 100? With each additional car sampled, our sampling distribution is less variable, meaning we've got a center at 48,000. We've got a normal curve, and the question is, looking at 100 at a time, how spread out is this normal curve? Our main three steps that we have on the normal curve, 1, 2, and 3 standard deviations away, that tells us how rare certain outcomes are. And let me call that 48 for space. So that's where we are. Is 100 going to make it, how spread out is that still going to make it? So the one formula that matters is the new standard deviation. This is the distribution of x bar on my graph, and the square root, the standard deviation of this distribution is the population standard deviation divided by the square root of the sample size. So I'm going to be dividing by 10. It's going to make 1,700. So on my graph, that's 1.7. So 48 and 1.7 is 49.7. Another 1.7 is 51.4, and then 53.1, I believe. And then 48 minus 1.7 is 46.3. And then I can't subtract, so I'm going to stop there. I found what I need to know. So my question is, what's the probability that my sample of 100 cars has a mileage on average over 50,000? So I can find that on my graph. 50,000 is, let's see, right in here somewhere. So this is the probability that I'm looking for. It looks like it's a pretty small chance, but it's not outrageous. So let's calculate it. What I'm looking for is the probability that I get 50,000 or more. So that's 50,000 to infinity with an actual center of 48,000. That 48, I shouldn't use a comma probably in that, and that's 58. It's 50,000, 48,000. Get the idea. And my standard deviation is 1,700. So this probability is coming up. That calculation, and I got 0.1197. So about 12% is the chance that I could go out and look at 100 cars, average up their mileage, and still get an average of over 50,000, assuming that the actual number is 48,000. So you can imagine what would happen if we went all the way up to, 1,000 cars. If you looked at 1,000 cars, this graph would be so tightly compacted that 50,000 would be very unlikely. The only thing that's going to be different in that calculation, if I were to do 1,000 cars, is my standard deviation will be adjusted to 17,000 over the square root of 1,000. root of 1,000 is 31.6 something. 17,000 divided by that, 537. So that would be about 0.5 on the scale. Let's get some of that down here. What if, and little n is our sample size. If it were 1,000, then this would be our calculation. Normal CDF, 50,000 to infinity, just saying what's the probability that the mileage is over 50,000. When in reality, it's 48,000. And you can actually type these calculations into your normal CDF command if you want. You could do 17,000 divided by square root of 1,000 in that command. You don't have to calculate it beforehand. Let me calculate that, and I'll let Dan answer in just a minute. Okay, so I've calculated that in my calculator, and this is actually, let's see, 0.0000995. So it's almost impossible. So let's see where we've gone. Remember, our two big facts. And the one that matters to us right now is the less variable. The more you look at, the higher your sample size, the less variable, which means that numbers far away from the mean, even if they're not very far away from the mean, become less and less likely. So think about that in terms of this problem. One car at a time, are we at all shocked if it has more than 50,000 miles? No, not a bit. I'd say most of the cars in the school parking lot have more than 50,000 miles. If you look at two at a time, are you shocked if they average out to over 50,000? No. Mine and almost any car, mine and a new car average out to more than 50,000. So that'll tell you how old my car is. If you look at 100 at a time, we're down to a 12% chance that they could average over 50,000, if in reality the average is 48,000. If you look at 1,000 at a time, it's almost impossible that they could average over 50,000, if in reality we're drawing from cars who average 48,000. So that's kind of, that's a lot of this semester really right there in a nutshell. We are looking to see how rare our outcome could be, or how likely our outcome will be, assuming that the population is the way it is. And that gets more and more rare with a larger sample size, okay? And then we'll focus on that more normal part in class. We got a little demo of the central limit theorem. But for right now, you need to remember our new formulas. And really just one. The first one is just saying that we're going to center on our actual population mean, but this is the important formula for this section. So that's it. That's it for Chapter 9, actually. There's just 3 sections. We're going to be getting ready for a quiz or test soon. And I will see you in class. I'm out.